Now maybe we're interested in calculating the pH of a basic solution. So maybe we've got some, I don't know, some 0.12 molar potassium hydroxide, and we want to find the pH. And potassium hydroxide is a strong base, and so most hydroxides are pretty strong, at least most soluble ones that normally contain these group 1 cations such as lithium, sodium, potassium. And how do we find the pH of it? Well, we actually have a couple of different ways we can do it, but here's the traditional way. So the traditional way would be to say it's a strong base, so it completely breaks down, so 100% into ions. Got to know your polyatomic ions still, so KOH is K+, and that's monatomic, but OH-, that's polyatomic. And if it's 100% breakdown, that means that if there was 0.12 moles in a liter of KOH, when it breaks down, and since it's 1 to 1 to 1, remember our hands from back in the stoichiometry chapters, right? So one of these breaks down and makes one of these, so and also one of these, so that ratio would be exactly the same. So this is 0.12 molar. And how do we find the pH? The pH is the negative log of the H+ concentration. But we don't have the H+ concentration, we have the OH-. But recall that Kw, the water self-ionization constant, 10 to the minus 14 at room temperature, is equal to the concentration of H+ times the concentration of OH-. And so if you have the concentration of OH- and you have Kw and you need H+ in order to find the pH, then you can use this equation, you can rearrange, you can divide both sides by the hydroxide ion concentration, and the reason for that is that when everything cancels out, you get the H+ concentration, which is what we need. So that is 1 times 10 to the minus 14 over 0.12. It was a strong base, so we got to assume that the concentration of the base was the concentration of the basic ion here. Okay, and we go ahead and we do the math. And using that double E notation, so don't forget, right, your calculator is very, very handy. So times 10 to the power you can write as EE. So 8.3 EE minus 14 would be the answer there. And of course, it has units, I suppose. So it's moles per liter because it's a concentration. Is it acidic or is it basic? Well, this H+ concentration is very small compared to the OH- concentration. So if this is bigger than this, that means it is a basic solution. And most of us are familiar with pH. It's a lot easier to look. Is it above 7? It's basic. If it's below 7, it's acidic. So if we take the pH, we need the negative log of the H+ concentration. And this is the H+ concentration right here. And it's got 2 sig figs, so if we go ahead and negative log that, we get 13.08. So that's much higher than 7 on the pH scale. So that's very, very basic, which is what we'd expect. Potassium hydroxide is a very strong base. Now you might say that was kind of a long calculation. Maybe there's a faster way to do it. It turns out there's actually a faster way to do this kind of calculation. And I don't know. I mean, I suppose it's kind of a useful thing to know, and the derivation I don't think is very important, but I think that the bottom line is quite important, and it does show up an awful lot. So if you have blood chemistry done by your med lab, they'll probably report these concentrations in terms of P concentrations. So we should know how this works, and what we're going to do here, and again, you probably haven't taken too many logarithms in your math classes, but let me go ahead and take the negative log of each side. And if you take the negative log of each side, the left-hand side actually becomes 14, and the right-hand side becomes the negative log of H+. And one of the beautiful things about logarithms is that the log of two things times together is the log of each thing added together. So I got the negative log of H+ plus the negative log of OH-. And we've met the negative log of H+ before. Remember, we called this the pH. And 14, of course, well, I suppose that's a number between 13 and 15, so there's not much to say about that. But if you look at pH and you look at negative log H+, the H you can kind of see is related to the H+, and the P you can say is, oh, gosh, that's the negative log of the concentration of what comes after. So if you've got the negative log of OH-, you might call the negative log part P, and the OH- you might call OH. So we can rewrite this expression as follows. So 14 is the pH plus the POH. So we've got our P notation here. So in general, P means the negative log of the concentration of whatever comes next. So if you had something like PNA in your MedLab Tech results, right, that would probably be the negative log of your sodium ion concentrations. If you had something like PK, that would be the negative log of your potassium ion concentrations. So the P scale is very, very nice. And why is this very, very nice? Well, here's the thing. If you want to find the pH and you've got the hydroxide ion concentration, you can actually calculate the pOH and use it to solve for the pH. So why is this so nice? Well, our potassium hydroxide, we said, completely broke down. And so the concentration of potassium hydroxide is, because it's 100% dissociating, is the concentration of hydroxide. And, oh, sorry, I got an extra 0 on there. Let me go ahead and scratch. There we go. Don't need to grow extra significant figures here. And before we went through this dance, right, we went ahead and we said, well, we've got the OH minus concentration, and we can solve for H plus through this equation here. But you may have been tempted to go ahead and just negative log it. And if you did, you actually would have been sort of half right, because the negative log of OH minus is really easy to calculate. It's just the negative log of 0.12. And remember, right, that's what we're calling the pOH. So if we go ahead and do that, we get 0.92. And now if you go back to the fundamental equation right up here, and you see 14 is the pH plus the pOH, you're just asking yourself, right, what added to 0.92 gives you 14? So that's really just rearranging 14 minus the pOH. And of course, if the pOH is 0.92, we know the pH, right, must be 14 minus that, so that is 13.08, which is what we actually already did on the previous slide, but I think this is probably an easier way to do it. We can go to another strong base, and we can maybe apply it to a different situation, and you can tell me, do you think this is easier, or do you think it's more work? And either way, it just gives you another way to solve these kind of problems. So here's a nifty problem where we can use our idea of pOH. We've got calcium hydroxide, which is a strong base. So calcium hydroxide, if it's strong, that means that it's completely ionizing. It's completely breaking down. Calcium's in group 2, the alkaline earth metal, and the hydroxides, remember, right, from our full ionic and net ionic stuff, that they are breaking down, and they're not sticking together, right? Negative charges don't tend to hold together. So we're using a coefficient out front here. If it is 0.12 molar, and it 100% breaks down, that means the calcium will be 0.12 molar, but the hydroxide will be double that because it's breaking into 2 hydroxides for every 1 calcium hydroxide. So 2 times by 0.12 is 0.24 molar. Again, remember the osmolarity, right, would be the sum of all that stuff. We want to find the pH. The pH, of course, is the negative log of the H plus concentration, which we don't have, but we have the OH minus concentration, so that means we can get the pOH. And the pOH is just the negative log of the OH minus, so that is 0.24. Again, we leave off the units. We've got 2 significant figures, so if we take the log of that, we need to have 2 decimal places, which with rounding gives me 0.62. And again, assuming we're at room temperature, we know that the pH and the pOH add up to 14, so pH plus pOH is 14, and if this is 0.62, we can see this must be 13.38, so that they add together to give 14. So our pH is 13.38, and that is definitely basic. And if you remember our last problem, right, we had 0.12 molar KOH, and it had a pH of 13.08. And here we have 0.12 molar calcium hydroxide. And the calcium hydroxide, right, has a different pH. Its pH is 13.38. So on our pH scale, remember 7 is neutral, and greater than 7, right, is basic. Our KOH is coming in at 13.08. And if we switch to blue, maybe our calcium hydroxide is coming in at 13.38. So the calcium hydroxide has a higher pH. So if you like, it's more basic. So even though they have exactly the same concentration, right, the calcium hydroxide is 0.12 molar, the potassium hydroxide is 0.12 molar, so you might be tempted to think they're both strong bases and they both have the same concentration, so they should have the same pH. That's not true. The calcium hydroxide's got a larger pH. It's larger by a factor of, or by a number of 0.3 here, and the reason for that is that it gives 2 hydroxide ions when it dissolves, whereas the potassium hydroxide only gives off 1. And it's the hydroxide ion that makes the solution basic. So if it's given off twice as many of these, it's going to be twice as basic on an OH minus term, but of course in pH it's logarithmic, so it becomes 0.3 units more basic.